Hey everyone, I'm Madeline. I'm from Group 2. I'm going to be talking about the rankine cycle. I'm not going to say we completed it because we didn't. We just kind of took data off the computer because it's still broken. So if my data is a little confusing, I'm confused too because I didn't actually perform the experiment. So here we go. Kind of an outline. I'm going to go through the theory of what theoretically should have happened, the results of what actually happened in the data that we got, and kind of where uncertainty and error could come from. So the objective given to us for this project was to be able to understand the operation of a rankine cycle and complete collecting data that's associated with the performance of the rankine cycle to see basically how efficient is the rankine cycle that we have. So in theory, the water is pumped into the boiler where it's heated up and converted to steam, and then pumped into a turbine where it expands to actually spin the turbine. And the turbine is connected to a generator, which then it will be able to conduct its electrical power, or convert it to electrical power. And then again, it's repeated through the same cycle over and over again. So starting with the results that we have. So this is for the boiler. As you can see, it's very rocky. There's no steady state time. I tried to find the time where it was the most kind of consistent and not all over the place. There was kind of some outliers that were a little bit crazy. And for this conversion, all of the pressures that we were given were in PSI, so they had to be converted to KPA, or could have converted the temperature to Fahrenheit to get the correct calculations of enthalpy and entropy using the steam tables. I know we all miss those steam tables, so it's really, really fun to hang out with them again to find all of these values. And then for the flow rate, as you can see from this flow rate map, there was no consistent time of flow rate at all. This was kind of that same consistent time. I tried to stay consistent with the time seconds that we used. And during that time, the flow rate is kind of all over the place. I took an average to find where our kind of steady state would be, which is about 5.5 liters per minute, which is very, very low for a rankine cycle. For the turbine, this is inlet and outlet. As you can see, the inlet pressure is much higher than the outlet, which is expected because, as I said earlier, the steam expands in the turbine, so we have a lower pressure going out. So that does match up to the theory that we would expect to see. And then for the generator, we did have more of a steady state time for the DC voltage and amps that we have seen through the time second of our graph. And that was the time that I used to do the turbine work rate for the inlet and outlet. The work rate was fine by the change of enthalpy from the change of temperature in the turbine, which I think I have the calculation later on, to get a very, very, very low work rate for our turbine. So I'm not going to go through the whole theory of the rankine cycle system because James did an amazing job doing it earlier, so I really don't want to bore y'all again going through all the steps. But for the steps in the cycle going from 2 to 3, which if you can see in the little diagram is going through the steam generator, which has heat going in. We used the outlet, which was actually the turbine inlet, and then atmospheric pressure going into the steam generator, since it's coming from the water tank, to find the heat that was generated in the steam generator, which was around 2,000, a little bit higher than 2,000 kilojoules per kilogram. And then going to the next step from 3 to 4 in the cycle is going through the turbine, which again is generating that electric power, expanding the steam, lowering the pressure. So using the turbine inlet and turbine outlet enthalpies, we were to find the work that was done in the turbine. And again, there's a calculation for the work rate that I found earlier to get work at about 130. And then for the final part of it is going from after the turbine back to the beginning where the steam is reconverted into water vapor to start the cycle over again. The condenser outlet. The condenser inlet is the turbine outlet, so those state values were used to be the same to find the heat that was released from that process. So this is where you can tell ours is broken. So the thermal efficiency of the entire rankine cycle takes the enthalpy from the 3 cycles that I just went through over the cycle from the heat generated. So it's the work from the turbine, the work from the pump, over the heat generated in the boiler and to find our efficiency, which was 6%, which is extremely, extremely low for a Rankine cycle. Obviously, some of the uncertainty was we didn't actually do the experiment, so we don't know exactly what human error was completed during finding the data that I used, but the digital resolution of the different actual measurements were taken, as well as the instrumentation that we know was used to find the temperature and mass flow rate, have pretty low uncertainties. And the error, obviously the apparatus is broken, there's a leak in the boiler, and that is shown in the low flow rate that we had. In conclusion, obviously it could have been way more accurate, and there is data that's more accurate, but the energy is higher in the boiler than the turbine, which is expected because there's heat being added. There are lower temperatures and pressures as it moves through the cycle, which is expected because obviously the steam is expanding, it's being turned into energy, so the pressure is decreasing. And it is very not efficient. Any questions? Cool, maybe next semester this will be fixed.
Yeah, just look.